video, we're going to be checking out three kinematic practice problems, one that's constant velocity, one that's accelerated motion, and the third one, which is free fall motion, which is also a form of accelerated motion as well. Each one of these, we're going to talk about some different methods and techniques to accurately get a final numerical solution while using a bunch of different formulas as well. So let's go ahead and take a look at this first one in red. It says a train is traveling at 34 meters per second across a distance of 6,000 meters. Determine the time it takes to travel this distance. Now, the way it's worded, saying traveling 34 meters per second, it's indicating that's moving at a constant velocity. So we'll definitely be using the formula velocity equals delta x over t, because that's basically our only constant velocity formula. We know the train is traveling 34 meters per second, so we're going to go ahead and label it as our velocity. And then across a distance of 6,000 meters, which is equivalent to the delta x, which is the displacement. So it is displaced 6,000 meters. And then at the end, it says we're determining the time. So I have all of my variables laid out, all of my knowns and unknowns, and I know which formula I'm going to use. So I'm going to go ahead and place those things where they belong in the formula. And we have 34 meters per second equals 6,000 meters over t. And from there, we just want to make sure we isolate the t. We don't want the t in the denominator, so we're going to go ahead and multiply both sides by t to get it out of the denominator. And then from there, we just have one more step. We want to make sure that we cancel out our 34 meters per second so that the t is completely by itself. So we're going to divide both sides by 34. Since we're multiplying by 34, we are going to do that opposite operation. And then that leaves us with t equal to 6,000 meters divided by 34 meters per second. We're going to go ahead and place that into our calculator, divide them out, and then we get 176.47 seconds as our final answer. So that is going to be similar to the strategy we're going to use for the next two problems. We are going to identify our knowns and unknowns. And then for the other problems, we're going to identify which formula we want to use second. This one we could identify it first because that's the only constant velocity formula. Do a little bit of algebra, and then once we isolate that unknown variable, then we have our final solution. All right, so let's go ahead and clear that one out and then move to our second problem. For our second problem, we have a car that's traveling at 13 meters per second and it slows to a stop in 20 meters. What was its acceleration? So now I have my three main acceleration formulas on the screen, and we're going to go ahead and choose a formula after we label our knowns and unknown. So it's initially going at 13 meters per second, so we're going to call that our VI, our initial velocity. And it slows to a stop, so obviously that's implying that our final velocity is 0 meters per second in 20 meters, which is going to be our displacement, our delta x. Okay, and then we're looking for the acceleration. Now, all three of these formulas have acceleration in them, but we only want to choose the formula where we have everything except the a so that we can algebraically solve for the acceleration. If I'm taking a look at the first one, I don't have time. The second one also involves time too, so I'm going to see if the third one works. Do I have VF? Yes. Do I have VI? Yes. And delta x? Yes. So I'm going to go ahead and use that third formula. When I place everything in there, I get 0 squared equals 13 squared plus 2 times a times delta x. And what I'm going to do is condense those numbers a bit. And I'm going to square my 0, which comes out to 0. I'm going to square 13, which comes out to 169. And then for these three numbers, since the order in which you multiply numbers doesn't matter, I'm going to go ahead and, oh, whoops, I didn't put the 20 in here. So this is 20 meters. I'm going to go ahead and combine the 2 and the 20, and then that would make it 40A. Now from there, you want to make sure you don't ignore the 0. Sometimes people just toss the 0 because they are seeing that it has no value there, but it's part of our setup. So we want to make sure we move the 169 first. So subtract 169 from both sides, and that leaves us with negative 169 equals 40 times a. And then we can go ahead and divide both sides by 40 so that the a is all by itself. And then we have a equal to negative 169 divided by 40, which is negative 4.225. So I'm going to round it to 223 meters per second squared. And it does come out negative because the acceleration is directed in the negative direction because the car is slowing down to a stop, so it should naturally come out negative. So in this case, we did the similar steps that we did for the first one, except we labeled our variables and our unknown first before selecting this third equation, and then we went ahead and did the algebraic steps to bring us to our solution. So let's go ahead and move to our last question. For our last question, it says a ball is thrown up with a velocity of 11 meters per second and rises for 2 seconds. Determine its height and its final velocity. So for this one, we have a few different things going on here. Because it's something that's moving through the air, we're going to assume that's a free fall question, which means it's only under the influence of gravity. In that case, the acceleration is negative 9.8 meters per second squared. So with these types of problems, there are a lot more values that you may use that aren't explicitly written in the problem. So it's thrown up with a velocity of 11, so that's our starting. VI equals 11 meters per second, and it rises for 2 seconds. That sounds like the time. I'm going to slide my A down here so it's in my list of things. And we're going to determine its height, which we'll call that a delta y instead of a delta x because it's a displacement in the vertical direction. And then we're eventually going to find the final velocity as well. So we're going to hold that thought and then do that second. All right, so if we want a displacement, we have to use the second or third formula. For my first one, I need VI, T, and A. So that one actually works. So I'm going to go ahead and set it up. Delta y equals VI times T plus 1/2 negative 9.8 T squared. All right, from there, 11 times 2 is 22. And then I'm just going to put minus because I know this is going to turn into a negative number because of the negative 9.8. So then I'm going to subtract 19.6, and then that's going to give me a delta y of 2.4 meters. All right, now from there, I can go ahead and add that to my list of things and put down that 2.4 meters. And then when I go to my final question, looking for the VF, I have every variable I could possibly need. So as long as the formula has a VF in it, I'm able to use it. So I could use the first one or I could use the third one. It really wouldn't matter that much. So let me go ahead and use the first one because we haven't used that one in this video yet. So I'm going to go with negative 9.8 equals VF minus 11 over 2. And then if I go ahead and get rid of the 2 first, that would be the most logical step so that we don't have a fraction. And then I have negative 19.6 equals VF minus 11. And then from there, just go ahead and add 11 to both sides. And then I get a final velocity of negative 8.6 meters per second, which actually indicates that the ball has already reached its peak and it is already coming back down. So this 2.4 meters is definitely not its peak height by any means because the ball already has risen up to its peak height and has fallen down a bit, but it's still 2.4 meters above where the person's hand is. And now it's heading downward at negative 8.6 meters per second. Now, if I did want to see how high it went, I could use a final velocity of 0 because it's going to have an instantaneous velocity of 0 right at its peak, and then I could find the delta y that way, but that's just not part of our problem. So I hope that was helpful to you in setting up and solving 3 different kinematic problems. Thank you for watching and listening.